Okay, so Sheila is building a water fountain for woolly mammoths using a large water tank that is completely sealed except for a very large tube that emerges from the bottom of the tank and extends upward at an angle of 45. The tube has a length of 1 meter, so it's 1 meter long, and the water level inside the tank is at a height 2 meters above the bottom of the tank. Assume the tank is large enough that the water level does not change appreciably as water flows out of it. So we're saying, okay, this is staying roughly at the same position as water leaves the tank. So the tank, there's a typo here. This shouldn't say greater, it should just say different, which is maybe a hint that it's lower. So let's see what we get. So water shoots out of the tube at a speed of 4 meters per second. There. What must be the pressure P in, so we want this, of the air inside the tank. And we can approximate atmospheric pressure, so PATM equals 10 to the 5th pascals. Tells us the density of water. And Marvin wants to remind you that the tube is not tiny and that this is not a kinematics problem. So Marvin's being very helpful here. So you'll notice that there's nothing about viscosity in this entire problem. So when you're trying to figure out what equations to use for fluid flow, you've got two options depending on the Reynolds number. So nothing in this problem has hinted at anything about a small Reynolds number. There's no mention of viscosity. There's no mention of anything tiny. There is a mention of density, which shows up in our column for high Reynolds number, which is hinting strongly that we should be using Bernoulli for this. So let's try that. So Bernoulli's equation tells us that if you look along a fluid flow, the pressure at some point plus rho GH plus 1/2 rho times the speed of the fluid squared is equal to some constant. So we can look at 2 points along this flow and compare this quantity. So what points should we pick? Well, we're interested in the pressure of the air inside the tank. So one point you could pick is this point right here at the top of the water, because the pressure there will be P in. So that will get P in into our equation. And then we have some information about the fluid flow at this point right here. So let's say this is point 1, and this right here is point 2. So let's do Bernoulli at point 1 and compare it to Bernoulli at point 2. So we'll have the pressure at 1 plus rho g, the height at 1, plus 1/2 rho v at 1 squared. It's going to be equal to the pressure at 2 plus rho g times the height at 2 plus 1/2 rho v2 squared. Now notice I didn't worry about what any of these things were when I wrote it down. I just said we're comparing Bernoulli at point 1 to Bernoulli at point 2. I just wrote down everything. Now we're going to figure out what these things are equal to. The only thing I've said so far is that I haven't said that these two pressures are equal, and I haven't said that the heights are the same or different, and I haven't said that the velocities are the same or different. I just labeled them with their numbers. Okay, so now let's take a look. So if we look at point 1, the pressure at point 1, P1, is P in. So I'll replace that with a P in. And then we need to figure out rho GH. So they give us this height. So let's put our coordinate y equals 0 at the bottom of the tank. So that means that H1 is equal to H. So this will be rho GH. Okay, so now what's the speed V1? Well, they told us that we can assume that the tank is big enough that the water level here doesn't change, which means that the speed at point 1 is 0. So this is 0. So we've got nothing for that term. At point 2, this point is open to the atmosphere. So the pressure there is atmospheric pressure. So P2 is just P ATM. What's the height at this point? We know that this is a distance L, and we know that this is an angle of 45 degrees. So we're really looking for this height right here, which is L times the sine of 45 degrees. So that is equal to the height, h2. So we're going to add rho g h2, which is L times the sine of 45 degrees. And then lastly, we need this term. So here we know that the speed of the fluid is 4 meters per second. So V2, just write it up here, V2 is 4 meters per second. Okay, so we want to solve for Pn. So let's solve for Pn, and then we can calculate a number. So Pn, we're just going to move this to the other side. So Pn is P ATM plus, so I'm going to subtract this from both sides. So this other side will actually, we could pull out the rho g. I'll just do all the math. Rho GL sine 45 degrees minus rho GH, and then we're adding half rho V2 squared. So just to make my calculator situation slightly easier, I'll pull this out. You don't have to do this. So now if you plug all the numbers in, so use rho ATM, you've got the density of water, you know what G is, it told you this was a meter, and blah, 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 etc., etc. Plug all those numbers in, you should get a pressure of 95,330 pascals, which is indeed less than the atmospheric pressure.